Okay, so we're going to go back to this example, the open system example, both because there was some questions about the M dots and the Q outs and things that Logan had. I don't have the work saved from what I was writing on the screen before, but I will just pull up the PDF of this this homework so you'll have it in the video, and we'll go through it kind of step by step and just talk about some of the aspects of it. So when we're talking about Exergy, it's a little bit difficult because sometimes we think about Exergy as being attached to the system itself, and we evaluate the Exergy as we evaluate this process or this thing that's happening in the system. And we do, but when we're looking at the best case scenario, we look at the system and the surroundings and we just take the base material of that and say, okay, how can we do this a different way? So if we have some sort of a mixing chamber process, it's mixing these fluids together and we're getting the end result is some other fluid at a different temperature. What we do is we say, okay, we could do it this way by mixing the fluid streams, but if we just look at the base components of this system, how much energy is available to do work in another way? Okay, so I think that sometimes trips us up and confuses us because when we're looking at the system, sometimes we're blinded by what we see and what is presented as a process. But when we're thinking about Exergy, we ignore the process that's happening to look at how much potential is there, if that makes sense. So this is a totally irreversible process, mixing two fluid streams together. But what we want to find out is how much potential there is in that system to do something else with that energy. Or in some cases, we look at the system and say, okay, how can we do this same process or have the same end result using a different process that might require less work input or have less irreversibility associated with it. Okay, so that's Exergy. So back to this mixing chamber example. Is it big enough that you can see, or should I zoom in? I'll zoom in a little. So we have water coming in at 2 different temperatures and leaving at a third temperature. So basically what we did is we had to look up all the properties of the 3 different fluid streams. The first one is using compressed liquid approximation. The superheated steam is just directly from the table, and then the stream coming out, we use again the compressed liquid approximation. So if we perform the energy balance on this, and I don't know what I wrote on the screen previously, but there was some issue with the signs. If you look at it here, we have a negative Q out on this side of the equation is equal to what's coming in minus what's coming out. So if we then we still, because we moved it over. Anyway. Okay, so when we perform this energy balance, this mass balance, we get it all together. We find the mass flow rate of the stream leaving, and then we perform the Exergy balance. So basically what we're doing is we're saying, okay, if we want to look at this system and find the max reversible power we could obtain if we used it for another purpose, then we analyze it using the Exergy balance. So we just say, okay, if it's a reversible steady flow system, then this side of the equation goes to 0. Our Exergy destruction will also go to 0 because we're looking at the best case scenario, which means that our Exergy coming in will be equal to our Exergy going out. So when we look at our Exergy coming in, we use the boundary in our surroundings, meaning that we are looking at this we're taking our boundary to be in the surroundings so that we don't have to worry about any heat interactions with the surroundings because this was a mixing chamber that was losing heat to the environment. So we balance those fluid streams using the Exergy balance, and we find that our reversible work is equal to this 4588 BTUs per minute. And then when we go to determine the Exergy destruction, we also look at it with the system boundary outside the system. So we're looking at the irreversibilities of the system, and we find that all of the Exergy that is available to do this work is destroyed because we just mix these fluid streams together and we don't actually produce any work. So if there were boundary work in this problem, or if there was some shaft that was being turned, or if something else was happening, then our Exergy destruction would not be the same as our work reversible. But because we're not doing anything useful with this system, then they are equal to one another. Yes.
What's that one symbol
This one?
Yeah, what's that?
That's the exergy of a fluid stream, or the flow exergy.
Okay.
So that's fluid stream 1, fluid stream 2, and fluid stream 3. So its units are kilojoules per kilogram, and it's for open systems only. For closed system, the exergy of the closed system on a per unit mass basis is this symbol. So this is for a closed system, and then this is for open system. And you can't see that on the video because I wrote it on the board, but there we go. Okay, so moving on, we're now talking about the second law of efficiency, which is a way for us to look at steady flow devices and compare them to their best possible selves. Because when we're looking at this second law of efficiency, we're looking at the exergy recovered divided by the exergy expended. So if we neglect changes in kinetic and potential energy, we assume the system is adiabatic, then we can just determine the simplified equations for each of these steady flow devices. So if we have an adiabatic steady flow turbine, then our work out is the exergy recovered, and the fluid, the difference between the exergy coming in and exergy coming out is the exergy expended. Okay, so we have this workout term divided by this psi 1 minus psi 2, which we can also say this psi 1 minus psi 2 is the reversible workout. So there's two different ways to think about this. One, we can think about the change in exergy as it flows through this turbine. The other is we can think about that we compare the workout to the reversible workout. And so that change in exergy, if we're assuming the turbine is adiabatic and there's and it's reversible, then that would be equal to just the change in the exergy of the fluid stream. So we don't have any heat losses to worry about, no friction or anything like that. We can also rewrite the equation if we go through different versions of, how to write the exergy destruction and workout and rearrange, which is shown in your text. I didn't do it for simplification here in this PowerPoint. You can also write it in terms of the entropy generated. So your second law of efficiency you can find in terms of exergy, or if you are analyzing the system from an exergy basis, you can also analyze the system from an entropy basis to find similar, it will be the same value, but it's a different methodology for finding the same efficiency. And then for an adiabatic compressor, we could also go through that process as well, where in this case the exergy recovered is from the fluid stream because we're gaining some ability to do work from this fluid as we run it through a compressor, and then divided through by the work in. So those equations for that. For a heat exchanger, the exergy expended is from the cold water stream, and the exergy recovered is from the hot water stream. And then if our heat exchanger is not adiabatic, meaning it's also losing heat to the outside, it becomes a little bit more complicated in the analysis. But we can still find the second law of efficiency of it using this equation here, where this temperature of the boundary is the temperature of the boundary of the heat exchanger, and the Q loss, Q dot loss, is the amount of heat or the rate of heat transfer to the surroundings that are at temperature T0. So T sub B is the temperature of the system or the boundary of the system. T sub 0 is this surroundings, and then the loss or the rate of the loss is how much heat is being lost per time out of this system. Okay, but again, we rely on the exergy of the cold and the hot fluid streams in order to analyze our second law efficiency. And then for a mixing chamber, similarly, if there's one hot stream, one cold stream, so in this mixing chamber, we're assuming we're mixing the same fluid just to get a different temperature. There's a different type of mixing chamber that involves chemical reactions. That's not for this. This is just to mediate the temperature of some flow stream. Then we can find the second law efficiency of that as well. So all of these are also in the text. They're in the PowerPoints that are online. But knowing the difference between how these apply and which equation goes to which steady flow device is very important. Okay, so let's do an example where we calculate the second law efficiency And in this case, we're going to use a steam turbine. So there are a lot of different components to this that we're going to figure out. Steam is entering a turbine steadily at 3 megapascals and 450 Celsius at a rate of 8 kilograms per second. And then it exits at 0.2 megapascals and 150 degrees Celsius. And then the steam turbine is also losing heat to the surroundings. And I think this is probably the first time we've analyzed a non-adiabatic turbine. But it's good to complicate things every once in a while. So we're going to assume kinetic and potential energy changes to be negligible. But we want to find the actual power output of this steam turbine, which is just a simple energy balance. The maximum possible power output, which we'll have to look at an Exergy balance. The second law efficiency, the rate of Exergy destroyed, and then the Exergy of the steam at the inlet. So we're going to look at how much power is actually coming out of this turbine, how much we could potentially get out of this turbine, the second law efficiency, so basically how it stacks up to itself when we compare the output to the max output, the rate of Exergy destroyed, so we're looking at how much is we're losing in the process, and then if we look at the Exergy of the steam at the inlet, we see the potential of the energy source. So if we run it through some other process rather than using it in a turbine, then we can look at it that way. Okay, so let's, yes?
The dead state temperature and pressure, how the book it says, you just assume it's 25, right, if it's not stated?
Yeah.
If it's not stated for like an ideal gas problem, you assume it's still 25?
Mm-hmm. Yeah, because it's just the temperature of the environment. So if you're, whatever, is regular ambient temperature is about 101 kilopascals, and 20 to 25 degrees Celsius is kind of like normal room temperature conditions. So if it's not explicitly stated, then you can just assume normal ambient conditions, that you're not operating in some like Sahara desert outside or something like that, or in a vacuum chamber, that it's just going to be kind of like normal room temperature, room pressure conditions. Okay, so the first thing that we need to do is perform the energy balance. So for a steady flow device, it's just Q dot in minus Q dot out plus work dot in minus work dot out is equal to m dot times H2 minus H1. So for this energy balance, do we have any Q in? No Q in. Do we have Q out? Yes. Do we have work in? Work out? Yes. Okay, so we have a negative Q dot out minus work dot out is equal to m dot times H2 minus H1. And if we go to our property tables, it's fairly easy for us to look up all of these values. So at state 1, 3 megapascals and 450 degrees Celsius, we have a superheated vapor. And at 0.2 megapascals and 150 degrees Celsius, when we come out, it's also still a superheated vapor. So we don't even have to calculate quality, which is kind of nice. So we find H1 is 3344.9 kilojoules per kilogram. And S1, because we'll need that later, is 7.0856 kilojoules per kilogram Kelvin. And then similarly, H2, we look that up, is 2769.1 kilojoules per kilogram. And S2, 7.2810 kilojoules per kilogram Kelvin. So we can solve this equation in terms of work dot out. That's what we're solving for in part A. So work dot out is equal to a negative Q dot out plus m dot times H1 minus H2. And if we plug in all the numbers for that using the enthalpy values and the Q that's given to us in the problem of 300 kilowatts, then we find that our work dot out is 4306 kilowatts. So this is the actual work per unit time produced by this turbine. Okay, so what we want to find now is the maximum potential work that could be created or generated using this turbine. So now if we perform, instead of an energy balance, we perform an exergy balance. We have x dot in minus x dot out minus x dot destroyed is equal to this dx dt. And because it's a steady flow engineering device, this side of the equation goes to 0. Because we're looking at the best possible scenario, this part of the equation goes to 0 where there's not any exergy destruction. So we have x dot in is equal to x dot out. Okay, so let's talk about the terms that we have coming into our system. Okay, that'll still stay there. Okay, so what do we have coming in to our turbine? Okay, flow, right? So there's going to be some exergy associated with that flow coming into the turbine. And what's leaving the turbine? Flow and heat. Heat, right? Okay, but if we want to look at the best possible scenario for a turbine, it's going to be adiabatic. Okay, so we're going to say, all right, we're going to assume we're not destroying any exergy and that our turbine is adiabatic. So we ignore the fact that there's heat leaving our system. An alternate way of thinking about that, again, is drawing a boundary sufficiently large that it's just interacting with the surroundings. There's the heat transfer is within our system boundary, that it's an isolated system. Or so that's the two different ways to think about it. One is that I want the best turbine possible, so I'm ignoring the heat transfer. The other is I'm drawing my boundary sufficiently large. It's the same thing. Okay, so we have our x dot in is equal to x dot out. So coming in, we have mass flow times the flow exergy of state 1 is equal to the mass flow times the flow exergy of state 2 plus our work term. We have some reversible work output from this system. So we can say that our work dot reversible out is equal to m dot times this phi 1 minus, or psi 1 minus psi 2. So this can be written as m dot for a steady flow engineering device. It's h1 minus h2 minus t naught times s1 minus s2. Okay, so that's this term here. So if we plug in all the numbers for that, we find that our reversible work out is equal to 5072 kilowatts. Okay, so compared to what we had before, work actual was 4306 kilowatts. So it's higher, right? That's what we would expect. If you ever find a number that's lower for a work-producing device, you better go back and check because you've done something wrong. So then our second law second law efficiency is just equal to our exergy recovered over exergy expended, or our work out divided by our reversible work out. So we have 4306 kilowatts divided by 5072 kilowatts, which gives us 84.9%. Okay, so our second law efficiency for this turbine is actually fairly high. It's 84.9%. If we were to look at just the thermal efficiency of the turbine, it would be significantly lower than that. But remember, what we're doing is we're comparing this turbine to its own best possible self. So second law efficiencies are generally higher than you would find for regular thermal efficiencies. Yes?
For the equation that we rev out, what's the mass flow?
This, it's given in the problem. It's, yeah, it's given 8 kilograms per second. So this is when we're using a turbine, there's some work potential available, right? And so we're actually harnessing some of that and creating usable work. So Exergy in the beginning is some value. There's some potential of this energy source, and we're actually getting 4,306 kilowatts of that. So the Exergy recovered is the amount of Exergy that we turn into usable work. Yeah. Okay. Any other questions on that? Okay, so second law efficiency. So then if we want to find the Exergy destroyed in this case, we can just do the reversible work out minus the actual work out for a work producing device, and we find that it's 776 kilowatts. And then if we want to find the Exergy of the inlet state, this is part E, D, C, it's just equal to H1 minus H naught, so we're comparing it to the dead state, minus T naught times S1 minus S naught. Okay, so we looked up all the property values for that. We looked up the property values of this liquid at the dead state. So we find that it's 12.38 kilojoules per kilogram. So just to give you the dead state properties, because I didn't write those on the other screen, H naught is equal to H sub F at 25 degrees Celsius, because we're assuming if our turbine takes the liquid all the way to the ambient temperature rather than having a superheated steam coming out, which is 104.83 kilojoules per kilogram. And S naught is equal to S sub F at the same temperature, which is 0.3672 kilojoules per kilogram Kelvin. No, because if you're assuming that this turbine is operating in its water, and it goes down to the temperature and the pressure of the ambient conditions, it's going to be liquid water, right? So it's room temperature water at room temperature, pressure, room pressure, ambient pressure. So if it's liquid water, we'd use the compressed liquid approximation, which is where we go to the saturated liquid vapor mixture table and just use the sub F values. Because even though our pressure is lower than the saturation, or higher than the saturation pressure on those values, it will be approximately the same liquid properties, because water is incompressible and all that. Okay, any other questions on this? Okay, so that concludes the lecture for Tuesday. So our lecture for today, we're changing keeps doing this. Okay, so we're changing gears. We're now moving into chapter 9. So we've gotten out of Exergy. We will revisit Exergy a lot in the future, but it will be in the application of analyzing the devices that we see in the future. So in chapter 9, we're going to talk about now the power output from machines, essentially. So we're talking about power cycles, and we look at the Carnot cycle and the Otto cycle in this lesson, and then we'll continue on with diesel and Brayton and gas turbines and things like that in the next lecture. So moving right into it. A power cycle is just something that operates on the cycle and produces some net power output for us. So if we think about lawnmowers and chainsaws and cars and Stirling engines or steam engines or whatever it is, any kind of a power cycle, we're getting power out of the device. And when we strip them of their irreversibility, so we minimize friction, we minimize chemical reactions, we minimize heat losses, then we can closely approximate these actual cycles with some idealized version of itself. And so these allow us to analyze them in an easier manner without having to do experiments and build prototypes and have very specific conditions on our systems. We can look at them in general. And then it allows us to compare one system to another. And so while we don't always have the most accurate numerical values at the end of it, because it's simplified, we're going to receive values that are higher for work output than we would actually get in practice. But the same trends and concepts carry over. So if we are changing the volume, what happens to this power output? Or if we operate at a higher temperature, what happens? That even though the values may be slightly different, those same trends will apply as we make modifications to our design in the process. So again, idealized systems, we do this all the time in engineering and especially in thermodynamics, that perhaps the actual potato is not a complete sphere of water, but we can idealize it that way. And our actual cycle maybe doesn't have specific sharp corners at which point pressure or volume changes, but we just make an approximation that allows us to analyze it a little bit easier. So some of those common simplifications that we've seen all throughout is that we imagine that we're in a world without friction. We also assume that the compression and expansion processes are happening at a sufficiently moderate rate so that we don't have vast changes in the properties across the control volume. So our compression happens so that we don't have any kind of fluctuation or oscillation in property values, and that things change at the same rate all across the control volume. We assume heat transfer is not a problem, and a lot of times we just completely ignore kinetic and potential energies because in most cases they're negligible compared to the other energy terms that we're more worried about. And we like to use property diagrams to get a visual representation of what we're doing. And for power cycles, they're especially important because the area enclosed is equal to the net work. So if we have some process that's operating in a region, and let's say that instead of going all the way up to there, it only goes there. Okay, if we were to compare those two processes one to another using their property diagrams, just by looking at it, we can tell that we're getting a lower network output than if we use the first process. And then we can say, okay, well, it appears to me that the reason we're getting lower network output is because we're only operating up to this pressure. Well, let's increase up to this pressure and see what happens. Okay, so maybe we increase the area this way, but it's minimized by a decrease in the volume. So these property diagrams allow us to see how changes in our variables or our design characteristics can change our net power output. And we do this in simulation. It's not necessarily an experiment that we create this device with a certain volume and run the experiment and then create another one with a different volume. We can do it numerically so that we can analyze them. The heat addition processes on these diagrams will occur in the direction of increasing entropy, which should make sense if you think about it, because as you add heat to the system, you're increasing the motion of the molecules, there's more disorganized energy, so the entropy level is higher. And then the heat rejection process will occur in the direction of decreasing entropy. So as you reject heat from your system, your entropy should decrease as well. And then if we look at the ratio of the network to the net heat, that gives us the thermal efficiency. So the same as we've looked at before with previous devices and cycles, we can look at the thermal efficiency for these power cycles. And if you look at the area under the curve on a TS diagram, we can see that this is Q in, this is Q out, and then Q net gives us that area inside the curve on the TS diagram. So PV diagrams are good for us to look at the work net, and TS diagrams are good for us to look at the Q net. And the Carnot cycle we've talked about, we used it when we were talking about heat engines and heat pumps and refrigerators last semester. And it's a cycle that we like to analyze and use because it's very easy to analyze. It's a four-step process that has very distinct and succinct processes involved. And it's also the absolute best cycle operating between any two temperature limits. So this is kind of like the holy grail of cycles. The Carnot cycle is the one that we compare a lot of the other cycles to. And so we can look at the efficiency of the Carnot cycle, and it's just a ratio of the temperatures in the system. And we've seen this before, so it should be pretty familiar. When we're analyzing these power cycles, there's some additional assumptions that we should make in order to make analysis even simpler. So we assume that the working fluid is a gas throughout the entire time, so that it's not changing phase. We don't have to worry about that like we do in a steam power engine. It's just a gas. And that the energy is provided by burning fuel with the system. So there's actually internal combustion happening, but instead of modeling this internal combustion, we just say, okay, this is our heat input to the system. We're going to look at it as a closed system with some heat input. And then we do the same thing for the exhaust, that instead of exhausting a mixture of gas and fuel, we're saying, okay, we're just going to have a heat rejection process. So it's a simplification of this cycle, and any process that is operating under these conditions we call the air standard cycle. So we assume air is the working fluid, that it doesn't change state, that the combustion process is modeled by heat in, exhaust is modeled by heat out, and we don't need to worry about that. And then an additional simplification that we can make is that if we're using C sub P and C sub V values at room temperature, then we call it the cold air standard assumptions. Okay? So these assumptions are applicable and valid to any of these gas power cycles that we'll analyze in Chapter 10, or Chapter 9, I guess we're in. And so we're just assuming that we're following the air standard assumptions in all of these problems. So terminology, again, this is review from last semester, but we'll go into more depth when we actually look at how to analyze these systems. So top dead center is the position of the piston when it forms the smallest volume. So this is the volume at top dead center. So it's the distance between these valves and the piston itself. Bottom dead center is when it forms the largest volume. So it's this entire volume here. And the stroke is the linear distance between top dead center and bottom dead center. So these two components are volumes. This one is just a unit of length. The piston diameter is just the bore. And then the intake valve and the exhaust valve are important just for our understanding of these devices, but when we analyze them in the idealized cycle, we don't worry about the intake and the exhaust. The clearance volume is the volume formed when the piston is at top dead center, and the displacement volume is the distance that is displaced as we move from bottom dead center to top dead center. And so this is not the same thing as the max volume, which is this entire component. The displacement volume is just the difference between the volume at bottom dead center and the volume at top dead center. And then this is called the compression ratio, R, which is the ratio of volumes. And then the mean effective pressure is a pressure that we use when we're analyzing these systems because the pressure is changing throughout. And to look at one system and compare it to another, we can use this mean effective pressure, which we say, okay, I know the pressure is changing, but what's the work output that we would get if we were to just assume some constant average pressure during this entire process? So if we're looking at the boundary work of a piston cylinder device, it's equal to P times V2 minus V1. Well, if this pressure is not constant, as it is in these processes, we can replace that with a mean effective pressure and find the difference in the max and min volume to determine how much work is being output from the system. Okay. Auto ignition is premature ignition of the fuel when the temperature is raised above the self-ignition temperature. And this is desirable in a diesel engine. It is very undesirable in a gas engine. You want spark ignition. And engine knock is what happens when that auto ignition occurs. And there's a couple of videos on there. They're not super informative, and we're shorter on time today than we would have been. But basically, it is a video of the noise that you hear when engine knock occurs. And despite what it sounds like, knock doesn't sound like a knock. It's just like a little like throaty kind of purr sound. But you can look up videos on that. And then octane in fuel is what helps the engines to prevent auto ignition and knock. So the higher octane fuels will have a higher auto ignition temperature, so that knock doesn't happen. So in performance vehicles that have high compression ratios, higher octane fuel is necessary. And an interesting note on that, as your car gets older, your compression ratio actually changes, because the clearance volume within your cylinder changes, and then as the piston is worn out and the bore changes, that your compression ratio can increase. So older cars that have a problem with knock need higher octane fuels. Usually when we have an old car, we don't care, and so we give it the cheapest gas possible, right? Well, if you're having a problem with knock, increasing the octane will be a good first step. So the two different types of reciprocating engines we mentioned just a minute ago, there's the spark ignition, where we have this air-fuel mixture within the chamber that's ignited by an actual spark from a spark plug. And then compression ignition, which is used in diesel systems. The fuel is injected into this chamber as the piston is compressed, so that it's already above the ignition temperature when that fuel is sprayed in, and it self-ignites. And that's the primary difference between how a gas and a diesel engine run, and why it's so bad if you accidentally put gas into a diesel car, because you'll have premature ignition all over the place. I don't know where my picture went. Okay, so the Otto cycle is the cycle that we use to approximate the best power cycle for a spark ignition engine. And so it consists of four strokes: intake, compression, power, and exhaust. And I don't know how to make my mouse click on stuff. No, it just wants to draw. I don't know how to get out of there. This one? Nope. See, it's like you're down the rabbit hole, you can't get out. The whole computer? Thanks. That's good advice, Logan. Okay, so there's another video there that I can't show. Now I can't get this back. Hold on. Okay. Stupid computer problems. Won't even erase now. I gotta do it with a mouse? Is that what it's telling me? Come on. Oh, it's lame. Okay, so they're the engines. I know what I can do. Hold on. I'll just go override. It's what?
Last video, wasn't it up on that smarting?
No, that didn't work. It actually was just trying to drag and select stuff. So automated engines. I can outsmart the computer. Okay, so this is a 4-stroke engine, and if we slow it down, we can watch it. So we have intake of an air-fuel mixture, compression, spark, and then exhaust. So if we just watch it really slow, we're intaking an air-fuel mixture, compressing it, the spark occurs, which forces the piston back down. That's your power stroke. And then we exhaust that, the combustion byproducts out the side. So this was first developed by Nicholas Otto in 1876. It's known as the Otto cycle. And it's the one that we use as it's our Carnot cycle version for gas power cycles. Ooh, that's not where I want to be. There, okay. Okay, so we can look at the Otto cycle on our diagram. This is what it actually looks like here. So this is the Otto cycle in actuality, and this is what our approximated version of it looks like. So you notice here that we actually have more than 4 things happening because we have an intake and an exhaust that we don't necessarily model on this diagram here. There is a modified version of it where we can look at it, and I show that later. The 2-stroke engine does the same thing, but only in 2 strokes. So if we look at the automated engine's 2-stroke, slow it down. Okay, so you can see that this crankshaft here is sealed, and there's this little valve here that's covered and uncovered by the piston. So it's letting in this air-fuel mixture. It goes into this cylinder, comes down. The gas byproducts are vented out while more is allowed to come in. And then as it compresses and the spark happens, then the piston is forced down again. That's a little too slow. So the 2-stroke engine has a power stroke every other stroke, whereas the 4-stroke engine has a power stroke every 4th stroke. So the power output to weight ratio for a 2-stroke engine is much higher. The problem arises because, as you can see in this diagram, that sometimes, I'll pause it right. Okay, so sometimes as we're venting these byproducts of combustion, we also vent unspent fuel. And additionally, because this combustion process occurs a little bit with less control, some of this fuel is not completely combusted because you're combusting as you're also bringing in more fuel. So the 2-stroke engine has gone out of favor for automobile production, even though it has a high power to weight ratio, simply because it's where am I? That one. It's difficult to pass emissions standards. There's my picture. Okay. However, there have been a couple of recent upticks in the use of 2-stroke engines in motorcycles, and both Honda and KTM have patents in the work in just the last couple of years that are pretty interesting. With the Honda patent, they have their fuel injector here, and so they want to, the idea is to spray the fuel onto the back of the cylinder. So rather than having the fuel injectors at the top where the venting happens to the side, they spray the fuel to the back of the cylinder as the piston is almost to the top dead center, so the self-ignition will occur at that point. So if they're able to spray that fuel in and have it combust completely, then the emission byproducts are a lot cleaner. One, because it's a more complete combustion, and also because there's not additional fuel coming in as you exhaust. So by doing that, they're able to get very high power to weight ratios, but still also pass emission standards. And then this KTM design, the difference between it and some of the others is that the fuel injection happens in the intake. So as they're intaking air for the piston cylinder to move down, that's when they would inject the fuel into the system. So it's after the exhaust has already happened, and so there's less chance of expelling uncombusted fuel to the environment. So again, it's to improve emission standards, or to comply with emission standards while still getting the benefits of a 4-stroke or 2-stroke engine.
So the Honda engine, that is still manually ignited. It does have a spark plug, or is it auto?
I think it still has a spark plug. If it's a gas engine, I would bet it has a spark plug. Yeah. But the spark is happening right after it sprays, and the fuel is already in the cylinder when it's almost all the way compressed. So they can get higher compression ratios that way, and they can reduce the emission byproducts. So kind of interesting, and neither of these are in production yet. They're both proposed, but these patents just came out just in the last couple of years, so hopefully they're working on it. And that, I think a lot of the technology will change on a smaller scale first before it moves into the automotive industry. which is needed. And an interesting note too, when we were just over in Europe, they have some now diesel Peugeots that get over 100 miles per gallon. Just very lightweight, tiny cars with very, very good fuel efficiency that still meet the emission standards in Europe, but probably wouldn't meet them in the US. Okay, so the Otto cycle, we can look at it on a PV and a TS diagram. And the idealized version of it is that state 1 to 2 is an isentropic compression process. So this is as that piston cylinder is moving up. State 2 to 3 is just modeled as a constant volume heat addition. So this is modeling our combustion for us. State 3 to 4 is an isentropic expansion. And then state 4 to 1 is a constant volume heat rejection. So again, this doesn't fully encompass or demonstrate the open system that is an Otto or a gasoline engine, but it's a model that approximates it pretty closely. So we can perform a closed system energy balance on it because we're assuming that this working fluid is just operating in the cycle and it's just air. We're not looking at the combustion process. There's a whole class for IC engines that is not this class. Another modified version of it is to account for this intake and exhaust. So we have actually a 0 to 1 and a 1 to 0 where that happens. So this is another modified version of the Otto cycle, which has no net effect on the energy analysis because this process or this component of the process right here does not have any network output. Okay, it just repeats on the same line. But if we needed to model what happens as we intake and exhaust, then we could use the modified Otto cycle. We'd still get the same network output though, so really there's not a reason to have to do it this way when you're looking at just energy terms. The only exception would be as if you needed to know exactly what happens during intake and exhaust or how long it takes or something like that. That's a slide that's not supposed to be there. Okay, so we can look at the thermal efficiency of the Otto cycle where it's just Q out over Q in. And that's equal to this 1 minus T4 minus T1 over T3 minus T2. So if we're assuming it's an ideal gas, we could write Q out is equal to C sub P times T4 minus T1. And this would be Q in is equal to C sub V or C sub P times T3 minus T2. So the C's cancel out. We just are left with ratios of temperature. And because process 1 to 2 and 3 to 4 are isentropic, and 2 to 3 and 4 to 1 are constant volume for an ideal gas, then we can, based on the Gibbs equation, which we derived long, long time ago in chapter 5 and 6 and 7, we worked up to that with ideal gases and then the Gibbs equation. These hold true, okay? So it's only for isentropic ideal gas processes that these equations are valid. You couldn't use it for steam or water or refrigerant or anything else other than ideal gases undergoing an isentropic process. So we can substitute that all back into this equation for thermal efficiency, and we find that the thermal efficiency for the Otto cycle is just based on the compression ratio. So if the working fluid is air, K is equal to 1.4. And depending on our compression ratio, V1 over V2, we can determine how efficient our cycle will be. So higher compression ratios will mean higher efficiency, but higher compression ratios also lead to auto ignition, so we have to be careful about that. So if we want to talk about how to increase the efficiency of the Otto cycle, we can increase the compression ratio as mentioned previously, but we're limited by the onset of knock or auto ignition, which happens. So if we compress our gas to a very high pressure, then it will be above the ignition temperature of the gas and it will just self-ignite before the spark plug has a chance to spark. So this causes great problems in your vehicle with timing, and if it's if it's bad enough, you can actually have a lot of vibration in the engine, and then motor mounts start breaking and all sorts of other bad things. The other thing that we can do is increase the specific heat ratio. So if we're assuming it's air, then it's always just 1.4. But if we're looking at this in more in-depth analysis, and we can look at the octane or the ethanol, that's the word I'm looking for, the ethanol component of the fuel, that can change the specific heat ratio of the fuel. So if we have a higher ethanol fuel or lower ethanol fuel, or if we're using different types of fuel mixtures, we can adjust this ratio. But we're limited by what gases are available, what's available in the pump. Gas engines for a vehicle or a car are pretty limited. We could do something different if we were just designing some homebrew kind of engine with different fuels. And there's actually a pretty interesting video, I should have put it in here, where this guy just has this 4-stroke engine that he's using, and he just says, okay, what happens if I put all these different types of fuels in it? And then he videos it with a high-speed camera to see what happens with all these different types of fuels, everything from like gasoline to diesel to gas oil mixtures to just straight alcohol, like isopropyl alcohol. And it's kind of interesting. Yeah. Have you seen it? Yeah. So it's kind of neat, and it's it's just playing with this specific heat ratio basically, and then seeing what happens when you put that into your engine, which in some cases was not good because it was like on fire. So we have to be careful. Okay, so let's do an example with the ideal Otto cycle. And in this example, we have a compression ratio of 10. So compression ratio is the ratio of V1 over V2 is equal to the compression ratio. Okay, so we take in air at 100 kilopascals. So when we're talking about taking in air, it's at this initial point here, so the intake, and 35 degrees Celsius, and then the cycle repeats 2,000 times per minute. Assuming constant specific heats at room temperature, determine the thermal efficiency of the cycle and the rate of heat input if the cycle produces 80 kilowatts of power. So you'll find this will be a nice break from some of the things that we did previously. Not that one. I have to find it. Because these problems in Chapter 9 so far are going to be easier than what you encountered in Chapter 8. Okay, so our compression ratio is given to us as 10. And if we want to extend this problem a little bit, we can make it a little bit more difficult. So state 1, we have 35 degrees Celsius. But in these problems, when we're working with ideal gases, we know that we need to convert that to Kelvin. So it's 308 Kelvin, and this is equal to T sub L, or the low temperature in our system. So if we remember, for an isentropic process, which it is from state 1 to state 2, then this ratio, T2 over T1, is equal to V1 over V2 to the K minus 1. And in this case, our K is equal to 1.4 for air. So we can rearrange this equation and solve for T2 is equal to V1 over V2 to the K minus 1 multiplied by T1. So if we plug in the numbers for that, our compression ratio is 10. So we have 10 to the 0.4 multiplied by 308 Kelvin. That gives us T2 equal to 773.7 Kelvin. So then our thermal efficiency is equal to 1 minus T sub L over T sub H, which is equal to 1 minus 308 over 773.7 Kelvin, which gives us a thermal efficiency of 60.2%. Okay, so that's one way to find the thermal efficiency of the Otto cycle for an ideal gas with isentropic processes. The other way, which is the shortcut, which we looked at on a previous slide, is just that it's 1 over 1 oh no, 1 minus 1 over R to the K minus 1. So if we just know the compression ratio, instead of going through this process, we've done it algebraically in there. 1 minus 1 over 10 to the 0.4 gives us the same value, 60.2%. Okay, so those two methods are equivalent, assuming you're working with an isentropic process for an ideal gas, which we were. Okay, so we found the thermal efficiency. Thermal efficiency is also equal to the work net over Q dot in. So we can solve for Q dot in is equal to the work dot net over this thermal efficiency. So that's equal to 80 kilowatts divided by 0.602, which gives us 132.9 kilowatts. Okay, so in order to get 80 kilowatts of power out of this system, we have to put in this much heat. If we knew the type of fuel we were using, we could know, or we could find the heating value of the fuel and determine the mass flow rate of fuel that needs to be burned in order to provide this much heat. Okay, so it's not asked to do that in this problem, and you don't have to do it even on this homework, but just keep that in mind. So this represents a combustion process in a closed system, and it's just the heat that's coming from that combustion process. So even though combustion by necessity is an open system or an open process, we're representing it just by some net amount of heat that's transferred into our system. Okay, so that's it for today. Get started on your homework. Don't leave it to the end, because it's not a super difficult assignment, but it will take some time. So get working on it, and I will see you on Tuesday, homework in hand.